Space has perfect parking spots, invisible zones where objects can float forever without any fuel. You feel like you're sitting still right now, but you're actually racing through space faster than any bullet ever made. Tonight we're discovering how gravity creates these impossible safe harbors, and why they're about to become humanity's cosmic highways. Before we dive into these gravitational sweet spots, drop a comment about where you're listening from. If you enjoy these cosmic discoveries, consider subscribing. These explorations are meant to be shared. Here's something that sounds impossible. Take two massive objects spinning around each other. Add a third, much smaller object. Common sense says the small one should get flung away or crash into something. Instead, nature creates perfect parking spaces. Right now, thousands of space rocks are parked in these invisible zones. They've been there for billions of years. No engines, no fuel tanks. They just hover in perfect formation while racing through space. Think about this. These rocks are moving faster than fighter jets. Yet they never break formation. They never drift away from their spots. It's like finding a calm zone in the middle of a hurricane that never stops spinning. The secret is gravity from two massive objects creating balance points in space. These zones stay perfectly stable no matter how fast everything moves. A French mathematician figured this out in 1772 using nothing but pencil and paper. His name was Joseph Lagrange. He never owned a telescope. He just did math. Lagrange calculated something incredible. When two massive objects orbit each other, they always create exactly 5 balance points in the space around them. Always, no matter what size they are. Here's the amazing part. His math said these points would exist everywhere in the universe. Wherever two big things spin around each other, they automatically build these cosmic parking spots. It took over a century to prove he was right. In 1906, astronomers found a space rock sitting exactly where his equations predicted. They called it a chills. Math had become reality. This discovery revealed something profound about space. It's not empty chaos. It's an organized system of invisible highways and rest stops that runs the entire universe. Imagine trying to balance on a seesaw with a giant on one end. Impossible, right? But what if there was a second giant pushing from the opposite direction? Suddenly you could find a perfect balance point. That's exactly what happens with these cosmic parking spots. Take our Sun and Jupiter. The Sun's gravity tries to pull small objects toward it. Jupiter's gravity pulls in a different direction. Add the spinning motion, and these three forces can perfectly cancel each other out. The result is zones where gravity essentially disappears. Small objects can sit there as if they're floating in a calm pool while cosmic forces rage all around them. Scientists call these spots where all the forces balance out equilibrium points. It's like finding the eye of a hurricane that never moves. Jupiter isn't traveling through space alone. It has an entire army of space rocks following it. They're called Trojan asteroids, and they've been Jupiter's faithful companions for billions of years. These rocks cluster at two specific spots. One group travels 60 degrees ahead of Jupiter. Another group follows 60 degrees behind. They form two massive cosmic caravans that never break formation. We're talking about thousands of asteroids here. Some are as big as mountains. Others are the size of city blocks, all of them staying in perfect formation while orbiting the Sun at incredible speeds. The most amazing part, they maintain this formation naturally. No guidance systems, no course corrections. Gravity does all the work. It's like discovering that nature has built the universe's most reliable fleet of escort vehicles. These Trojan asteroids prove that space has hidden structure we're only beginning to understand. Imagine parking your car and never needing to start the engine again. Not for years. Not for decades. Not ever. That's what these cosmic parking spots offer spacecraft. Space agencies have discovered they can position satellites at these points and barely use any fuel. The satellites just sit there, perfectly balanced, doing their jobs for years without burning hardly any propellant. This changes everything about space travel. Fuel is the heaviest, most expensive part of any space mission. These balance points eliminate that problem almost entirely. Think about the possibilities. Space telescopes that can operate for decades. Communication satellites that never need replacement. Deep space missions that can park and wait for the perfect moment to continue their journey. We're looking at the universe's natural refueling stations. Except they never run out of fuel because they don't need any. Not all cosmic parking spots are created equal. There are 5 of these balance points around every pair of massive objects, but only 2 of them actually work as reliable parking spaces. Scientists call the stable ones L4 and L5. These are the points that form triangles with the 2 massive objects. The other 3 points are like trying to balance a marble on top of a hill. One tiny push and everything falls apart. L4 and L5 are different. They're like valleys instead of hilltops. If something tries to push an object away from these points, natural forces gently guide it back. It's self-correcting parking. This stability is what makes L4 and L5 so valuable. You can put a spacecraft there and it will naturally want to stay put. Small disturbances actually make the position more stable, not less. The mathematical term is dynamically stable, but really it just means these spots are cosmic sweet spots that resist being disturbed. Here's where the physics gets really weird. These balance points only work because everything is spinning. If the Sun and Jupiter stopped moving, the parking spots would vanish instantly. The trick is thinking about space from the right perspective. Instead of watching from far away, imagine you're spinning along with Jupiter and the Sun. From this viewpoint, those cosmic parking spots look like they're standing perfectly still. Scientists call this a rotating reference frame. It's like sitting on a merry-go-round. From your seat, everything on the merry-go-round looks stationary, but to someone watching from outside, you're spinning rapidly. In these parking spots, centrifugal force and gravity balance each other perfectly. Centrifugal force is what pushes you outward when you go around a curve too fast. Gravity pulls inward. When they cancel out exactly, you get a stable hovering zone. This spinning balance is what keeps thousands of asteroids locked in formation for billions of years. It's physics turning chaos into perfect order. Space telescopes have found their perfect home in these cosmic parking spots. The James Webb Space Telescope sits at one right now, taking pictures of the deepest corners of the universe. These locations solve a major problem for space observatories. Most satellites orbit Earth, which means they regularly pass through Earth's shadow. When that happens, solar panels stop working and instruments get cold. Parking spots like L2 solve this completely. A telescope there never gets blocked by Earth's shadow. It has constant sunlight for power and an unobstructed view of deep space. Plus, it barely uses any fuel to stay in position. The result is space telescopes that can operate for decades instead of years. They can take longer exposures and make more precise measurements because they're not constantly adjusting their position. These cosmic parking spots have revolutionized our ability to study the universe. They've turned space-based astronomy from a short-term experiment into a permanent scientific outpost. The three-body problem has frustrated scientists for centuries. Predicting how three objects will move when they're all pulling on each other gravitationally is incredibly complicated. Small changes lead to completely different outcomes. But these balances represent something remarkable. They're places where this chaotic system finds perfect order. Nature has solved one of physics' most difficult puzzles by creating islands of stability in a sea of complexity. It's like discovering that a violent storm naturally creates calm spots that never move. The chaos organizes itself into patterns we can predict and use. This elegance extends throughout the universe. Every pair of orbiting objects creates these balance points. Double star systems, planet and moon pairs, even galaxies orbiting each other. The same mathematical rules apply everywhere. What seemed like an impossibly complex problem turns out to have a beautiful, universal solution built right into the fabric of space and time. The moon's orbit creates its own set of cosmic parking spots with Earth. These are about to become humanity's first interplanetary truck stops. Space agencies are already planning to build stations at these Earth-Moon balance points. They'll serve as staging areas for lunar missions and eventual trips to Mars. Crews can park there, transfer between vehicles, and prepare for the next leg of their journey. These locations cut fuel costs dramatically. Instead of fighting gravity all the way to the moon, spacecraft can hop from one balance point to another using minimal energy. It's like having rest stops on a cosmic highway. The strategic value is enormous. Control these balance points, and you control the space lanes between Earth and Moon. They're the high ground of space expansion. Within decades, these cosmic parking spots could become bustling hubs of human activity. The first permanent outposts in our expansion beyond Earth, all made possible by the mathematics of celestial mechanics. This entire story represents one of science's greatest triumphs. A mathematician with 18th century tools predicted something that wouldn't be confirmed for over 130 years. Pure math revealed hidden architecture in space before anyone could see it. The equations were beautiful in their simplicity, just basic laws of gravity and motion, extended to three objects instead of two. Yet from this simple mathematics came predictions that seemed almost magical. When astronomers finally found the first Trojan asteroid exactly where the math said it should be, it validated something profound about the universe. Reality follows mathematical rules with stunning precision. Today, we're using these 250-year-old equations to plan missions to other planets. Ancient mathematics has become the foundation for humanity's expansion into space. It's a reminder that the universe isn't random chaos. It's an elegantly structured system where mathematical beauty and physical reality are the same thing. Between the Sun and Jupiter lies the most unstable parking spot in the solar system. This is L1, the first balance point. Objects that end up here face a cosmic tug-of-war they can never win. Picture standing exactly between two massive magnets pulling in opposite directions. One tiny step toward either magnet and you get yanked away violently. That's exactly what happens at L1. The Sun's gravity pulls objects toward it. Jupiter's gravity pulls the other way. Right in between them sits this precarious balance point where the forces exactly cancel out. But it's like balancing on a knife's edge. Any small disturbance sends objects tumbling away from L1 forever. A passing comet, solar wind, even radiation pressure can knock something out of this position. Once it starts falling, there's no going back. L1 represents the universe's most unreliable parking spot, where perfect balance becomes perfect instability. Travel past Jupiter, and you'll find L2, a balance point that seems to break the rules of physics. Here, gravity from both the Sun and Jupiter actually helps objects orbit faster, not slower. Common sense says objects farther from the Sun should orbit more slowly. That's how planetary motion normally works. But L2 creates an exception to this cosmic speed limit. At this location, Jupiter's gravity joins forces with the Sun's pull. Together, they give objects the extra boost they need to keep up with Jupiter's orbital speed. It's like having two engines instead of one. The result is synchronized motion that shouldn't be possible. Objects at L2 stay perfectly aligned with Jupiter as both race around the Sun together. They form a cosmic convoy that maintains formation across millions of miles. This cooperative gravity makes L2 one of space's most useful parking spots for human spacecraft. Directly opposite Jupiter, hidden behind the Sun, sits the most mysterious balance point of all. L3 creates a perfect mirror image of Jupiter's position, maintaining exact symmetry as the solar system spins. No human eyes have ever seen this region directly. The Sun's blaze completely blocks our view of L3. We know it exists only through mathematics and indirect observation. This hidden zone maintains a delicate dance with Jupiter. As Jupiter moves around the Sun, L3 moves in perfect synchronization on the opposite side. They're like cosmic dance partners separated by the Sun's bulk. Science fiction writers love L3 because it's the perfect hiding spot for secret planets. In reality, this balance point is just as unstable as L1 and L2. Any objects there would eventually drift away. L3 remains the solar system's most elusive balance point, forever hidden in the Sun's glare yet mathematically certain to exist. Here's the surprising truth about cosmic parking spots. Out of 5 balance points around any 2 massive objects, only 2 are actually reliable. The other 3 are elaborate traps disguised as safe harbors. Scientists discovered this through mathematical analysis of stability. L1, L2, and L3 are what they call saddle points. Imagine trying to balance a marble on top of an upside-down bowl. One tiny push, and it rolls away forever. LL4 and L5 are completely different. They're like valleys instead of hilltops. If something tries to push an object away from these points, natural forces gently guide it back home. They're self-correcting. This difference in stability changes everything. You can park a spacecraft at L4 or L5, and it will stay put for millions of years. Park the same spacecraft at L1, L2, or L3, and you'll need constant fuel to keep it from drifting away. Only 2 out of 5 cosmic parking spots pass the long-term stability test. L4 and L5 reveal nature's hidden love affair with perfect triangles. These 2 balance points form equilateral triangles with the Sun and Jupiter, creating one of space's most beautiful geometric arrangements. An equilateral triangle has all 3 sides exactly the same length. It's one of geometry's most stable shapes. Nature has built this mathematical perfection into the structure of space itself. From above the solar system, you'd see Jupiter at one corner of the triangle. The Sun sits at the second corner. L4 and L5 occupy the third corners of 2 separate triangles, one ahead of Jupiter and one behind. This triangular arrangement isn't random. It emerges naturally from the mathematics of gravitational interaction. When 3 objects form perfect triangles, they create stable relationships that can last forever. The universe has embedded geometric beauty directly into the laws of physics, making L4 and L5 monuments to mathematical elegance. Finding these cosmic parking spots requires solving one of physics' most elegant equations. The answer always comes out the same: 60 degrees. This magic number unlocks the location of nature's most stable balance points. Start with a line connecting the Sun and Jupiter. Now rotate exactly 60 degrees from this line. That's where you'll find L4. Rotate 60 degrees in the opposite direction and you've located L5. This 60-degree rule works everywhere in the universe. Binary stars, planet-moon systems, even galaxies orbiting each other. The mathematics never changes, regardless of size or distance. The calculation relies on basic trigonometry that students learn in high school. Yet this simple math reveals cosmic architecture that spans light years. It's a reminder that the universe follows surprisingly simple rules. 60 degrees represents the mathematical signature of gravitational harmony written across the cosmos. Space around any two massive objects resembles a landscape of invisible hills and valleys. This energy terrain determines where objects can park safely and where they'll tumble into chaos. Imagine this landscape like a topographical map. High points represent places where objects need lots of energy to stay put. Low points are natural parking areas where objects settle comfortably. L1, L2, and L3 sit on top of energy hills. Objects there are constantly trying to roll downhill and escape. L4 and L5 nestle in energy valleys where objects naturally want to remain. Scientists call this the gravitational potential energy surface. It's like having a detailed map of every cosmic parking spot, gas station, and dangerous curve in the solar system. This energy landscape reveals why some balance points work and others don't. Nature has built a complex road system in space, complete with safe rest stops and treacherous mountain passes. Everything changes when you imagine yourself spinning along with Jupiter and the Sun. From this rotating viewpoint, the cosmic parking spots look like they're standing perfectly still in space. Scientists call this a rotating reference frame. It's like sitting on a merry-go-round and watching the horses in front of you. To someone on the ground, you're all spinning rapidly. But from your seat, those horses look motionless. In this spinning perspective, new forces appear that don't exist for outside observers. Centrifugal force pushes objects outward. Coriolis force makes moving objects curve. These imaginary forces help create the balance points. The mathematics becomes much simpler in the rotating frame. What looks like complex orbital motion from the outside becomes a simple balance of forces from the inside. This perspective shift transforms chaotic motion into elegant stillness, revealing the hidden simplicity behind cosmic mechanics. The size difference between two orbiting objects determines everything about their balance points. Make the smaller object too big, and the parking spots vanish completely. For cosmic parking spots to exist, one object must be at least 25 times more massive than the other. This isn't arbitrary. It comes from the mathematics of gravitational interaction and orbital stability. Jupiter outweighs the Sun by a factor of about 1,000. This huge mass difference creates rock-solid stability at L4 and L5. But if Jupiter were much larger compared to the Sun, these balance points would disappear. The mass ratio also determines exactly where the balance points sit and how stable they are. Change the ratio and you change the entire gravitational architecture of the system. This mass requirement explains why cosmic parking spots are special. They only exist when the universe creates the perfect size relationship between orbiting objects. In the rotating world of Jupiter and the Sun, gravity alone doesn't tell the whole story. Centrifugal force joins the mix. creating a combined force field that reshapes the entire energy landscape of space. This merged force field is called the effective potential. It combines real gravity with the imaginary centrifugal force that appears in rotating reference frames. The result is an entirely new map of cosmic hills and valleys. Places that looked stable under gravity alone become unstable when rotation is added. Other locations become more stable than ever. L4 and L5 emerge from this merger as the deepest, most stable valleys in the combined force field. They're like cosmic sinkholes that naturally collect and hold objects for billions of years. This effective potential reveals the true architecture of space around any rotating system, showing where nature has built its most reliable parking spots. Push an object away from L4 or L5 and something magical happens. Instead of drifting away forever, invisible forces gently guide it back to its original parking spot. It's like having a cosmic autopilot that never turns off. This restoring force works without any engines or guidance systems. Disturb an asteroid at L4 and gravitational forces automatically start pulling it back toward the balance point. The farther it drifts, the stronger the pull becomes. Think of it like a rubber band stretched between an object and its parking spot. The more you stretch it, the harder it pulls back. But instead of rubber, this restoring force comes from the precise balance of gravity and orbital motion. Most cosmic parking spots don't have this self-correcting ability. L1, L2, and L3 are like balancing on a tightrope. One small push and you fall off forever. L4 and L5 are like sitting in a bowl. Push yourself up the sides and you naturally roll back to the center. This automatic course correction is what makes L4 and L5 nature's most reliable parking spots in space. Objects near L4 and L5 don't just sit perfectly still. They perform a slow, graceful dance around their parking spots that can last for millions of years. Picture a figure skater spinning in a small circle on the ice. That's what asteroids do around these balance points. They trace out gentle oval paths, neither drifting away nor crashing into anything. It's orbital motion in miniature. Scientists call this motion libration. The word comes from the Latin term for balancing scales. Objects literally balance back and forth around the equilibrium point in long, lazy cycles. These cosmic dance moves are incredibly slow by human standards. One complete cycle might take decades or centuries to finish. From our perspective, the asteroids look nearly motionless, but they're actually performing an elegant ballet in space. This gentle oscillation proves that L4 and L5 aren't rigidly fixed points but rather flexible zones where objects can move safely within invisible boundaries. Here's a cosmic rule that determines whether balance points can exist at all. The smaller object must weigh at least 25 times less than the larger one. Cross this threshold and the parking spots vanish instantly. This isn't just a suggestion from nature. It's a hard mathematical limit built into the equations of orbital mechanics. Make Jupiter too big compared to the Sun and L4 and L5 would disappear completely. The mass ratio acts like a cosmic switch. Below 25:1, you get stable parking spots. Above that ratio, the gravitational forces become too chaotic to maintain balance points. It's an all-or-nothing proposition. Real solar systems easily meet this requirement. Jupiter weighs about 1,000 times less than the Sun. Earth weighs about 80 times less than the Sun. These ratios provide huge safety margins for stable balance points. This mass limit explains why cosmic parking spots are relatively rare. Nature must create the right size relationship between orbiting objects before these gravitational safe harbors can exist. What happens if you park a spacecraft slightly off target at L4 or L5? Mathematicians have proven that small errors stay small forever. This property is called Lyapunov stability, and it makes these parking spots incredibly forgiving. Launch your spacecraft toward L4 with a tiny navigation error. That mistake won't grow over time. In fact, the natural restoring forces will gradually correct the error and guide you closer to the perfect parking spot. This stability proof comes from advanced mathematics that analyzes how errors behave over time. For unstable systems, tiny mistakes grow into huge problems. For stable systems like L4 and L5, small errors remain manageable forever. The math works by examining what happens to nearby orbits. If all nearby trajectories stay close to each other, the system is stable. If they diverge rapidly, it's unstable. L4 and L5 pass this mathematical stability test with flying colors. This mathematical guarantee transforms L4 and L5 from theoretical curiosities into practical destinations for real space missions. Asteroids near L4 don't orbit in perfect circles. Instead, they trace out paths that look remarkably like tadpole tails when viewed from above the solar system. These tadpole orbits get their name from their distinctive shape. The asteroid starts near LO4, loops out in front of Jupiter, then curves back behind the balance point before returning to its starting position. The complete path resembles a cosmic tadpole swimming through space. The tadpole shape emerges from the complex interaction between Jupiter's gravity, the Sun's pull, and the asteroid's own orbital motion. Each force contributes to the overall path, creating these elegant curved trajectories. Different asteroids trace different tadpole shapes depending on their exact position and velocity. Some have narrow, elongated tails. Others draw wider, more circular paths. But they all share the same basic tadpole architecture. These orbits prove that L4 and L5 aren't point destinations, but rather extended neighborhoods where objects can roam freely within invisible boundaries. Give an asteroid enough energy near L4, and it won't just trace a simple tadpole path. Instead, it will embark on an epic journey that connects L4 to L5 through a horseshoe-shaped route around Jupiter. This horseshoe orbit represents one of space's most remarkable highways. The asteroid starts near L4, gradually drifts toward Jupiter, then swings around behind the planet to approach L5. After spending time near L5, it reverses course and returns to L4. The complete journey can take hundreds of years to finish. From our perspective, these asteroids appear to be slowly trading places between the two stable balance points. They're cosmic commuters on the universe's longest bus route. The horseshoe shape emerges when objects have just the right amount of energy to escape their local tadpole orbits, but not enough energy to leave the L4-L5 system entirely. They end up trapped in this figure-8 highway between both balance points. These horseshoe orbits reveal that L4 and L5 are connected by invisible gravitational roads that objects can travel for millions of years. In the rotating world of Jupiter and the Sun, moving objects experience a mysterious sideways push called the Coriolis effect. This phantom force helps stabilize the cosmic parking spots in ways that aren't obvious from the outside. The Coriolis effect only appears when you're spinning along with a rotating system. Try throwing a ball straight across a spinning merry-go-round, and it will curve to the side from your perspective. That sideways curve is the Coriolis effect in action. In space, this effect influences how objects move near L4 and L5. An asteroid drifting away from its balance point doesn't just feel a restoring pull back toward the center. It also experiences a Coriolis push that helps guide it into stable orbital patterns. This sideways force acts like cosmic guardrails on the gravitational highways near balance points. It prevents objects from wandering too far from their designated lanes and helps channel them into the tadpole and horseshoe orbits we observe. The Coriolis effect transforms simple gravitational attraction into a sophisticated guidance system that keeps objects safely parked at L4 and L5. Every cosmic parking spot has its own natural rhythm, like a cosmic tuning fork that vibrates at a specific frequency. This natural frequency determines how quickly objects oscillate around L4 and L5. Think of pushing someone on a playground swing. Push at the right rhythm and the swing goes higher. Push at the wrong rhythm and you interfere with the natural motion. L4 and L5 have their own natural swing rhythms built into the gravitational environment. Scientists can calculate this frequency using the masses of Jupiter and the Sun plus the distance between them. The math reveals exactly how fast objects should vibrate around the balance points. Observations of real asteroids confirm these theoretical predictions. Objects that vibrate at the natural frequency stay in stable orbits around L4 and L5. Objects that vibrate too fast or too slow eventually drift away from the parking spots. It's like cosmic natural selection favoring objects that match the environmental rhythm. This natural frequency acts as a cosmic quality control system that keeps only the most stable objects parked at the balance points. Objects at L4 and L5 are trapped by one of physics' most fundamental rules, energy conservation. Once parked at these balance points, they lack the energy needed to escape to anywhere else in the solar system. Energy conservation means that the total energy of any object stays constant unless something adds or removes energy. Think of it like having a fixed budget. You can spend money on different things, but your total spending can't exceed your income. For asteroids at L4 and L5, their total energy budget is just barely enough to move around within the local neighborhood. They don't have enough energy in the bank to buy passage to other parts of the solar system. This energy limit creates invisible prison walls around the balance points. Objects can move freely within these walls, tracing tadpole and horseshoe orbits. But they can never accumulate enough energy to break out completely. Energy conservation transforms L4 and L5 from temporary rest stops into permanent gravitational prisons that hold objects for billions of years. Deep mathematics provides an ironclad guarantee that most orbits near L4 and L5 will remain stable forever. This guarantee comes from the Km theorem, one of the most important stability proofs in all of physics. Km stands for Kolmogorov, Arnold, and Moser, the three mathematicians who proved this remarkable result. Their theorem shows that small disturbances to stable systems don't destroy the overall stability. They just create small wiggles in otherwise regular motion. The theorem applies perfectly to cosmic parking spots. Even if passing comets or solar storms disturb objects at L4 and L5, the overall stability remains intact. The disturbances create small changes in orbital paths, but they don't kick objects out of the parking spots entirely. This mathematical proof gives space mission planners confidence that spacecraft parked at L4 and L5 will stay put for decades or centuries. It's not just an educated guess, but a rigorous mathematical guarantee. The Km theorem elevates cosmic parking spots from promising ideas to certified safe harbors backed by the strongest possible mathematical foundation. Engineers have discovered a clever shortcut for analyzing stability at cosmic parking spots. Instead of solving the impossibly complex three-body problem exactly, they use linearization to get quick answers that are good enough for practical purposes. Linearization works by focusing only on small motions near the balance points. It's like analyzing how a car handles by testing only gentle turns instead of extreme maneuvers. You miss some details, but you get the essential information much faster. The technique converts the chaotic three-body equations into much simpler linear equations that engineers can solve with standard mathematical tools. These simplified equations reveal whether balance points are stable or unstable without requiring supercomputers. Real space missions use linearization analysis to design spacecraft trajectories and station-keeping maneuvers at L4 and L5. It provides the engineering precision needed to plan actual missions without getting lost in mathematical complexity. This practical approach bridges the gap between pure mathematical theory and real spacecraft operations at cosmic parking spots. The cosmic parking spots we've discussed exist in the flat plane where Jupiter orbits the Sun. But real space has 3 dimensions, and adding that third dimension makes L4 and 5 even more stable than expected. In 3-dimensional space, objects can move up and down relative to the orbital plane as well as forward and backward. This extra freedom might seem like it would make parking spots less stable. Instead, it creates additional restoring forces that help keep objects in place. Think of the orbital plane like the surface of a pond. Objects can bob up and down like corks on water while still maintaining their position relative to the shore. The up-down motion doesn't interfere with the left-right stability. Mathematical analysis shows that motion perpendicular to the orbital plane creates its own set of stable oscillations. Objects at L4 and L5 can vibrate vertically while maintaining their horizontal parking position. The 2 types of motion don't conflict with each other. This 3-dimensional stability makes cosmic parking spots even more reliable than originally predicted, providing multiple layers of gravitational security for parked objects. In 1906, a German astronomer spotted something impossible in his telescope. A faint point of light was keeping perfect pace with Jupiter. Staying exactly 60 degrees ahead of the giant planet, he had just discovered the first proof that cosmic parking spots actually exist. The astronomer named this space rock Achilles, after the legendary Greek warrior. For 130 years, Lagrange's mathematical predictions had remained unproven theory. Achilles changed everything by becoming the first confirmed resident of a cosmic balance point. This discovery sent shock waves through the scientific community. Here was a chunk of rock and metal following Jupiter around the Sun in perfect formation. No engines, no fuel, no guidance system. Just pure gravitational mechanics doing exactly what the math predicted. Achilles wasn't alone in space. As telescopes improved, astronomers found hundreds more asteroids camping out at Jupiter's L4 and L5 points. Each discovery validated Lagrange's centuries-old calculations in spectacular fashion. The first Trojan asteroid transformed abstract mathematics into observable reality, proving that the universe really does follow mathematical laws with stunning precision. Every asteroid parked at Jupiter's L4 point bears the name of a Greek hero from the legendary Trojan War. Achilles leads this celestial army, followed by Patroclus, Ajax, Odysseus, and dozens of other mythical warriors. This naming convention wasn't accidental. Astronomers decided that asteroids sharing Jupiter's orbital space deserved names from humanity's greatest epic stories. The L4 asteroids became the Greek camp, forever stationed ahead of Jupiter in its cosmic march around the Sun. Each name tells a story from ancient literature. Patroclus was Achilles' closest friend. Ajax carried an unbreakable shield. Odysseus masterminded the famous wooden horse strategy. These space rocks carry the legacy of heroes who fought beneath the walls of Troy. The tradition continues today. Every newly discovered asteroid at L4 automatically receives a Greek hero's name. It's astronomy's way of honoring both ancient storytelling and modern scientific achievement. This celestial Greek camp proves that even in the cold vacuum of space, human culture and scientific discovery can merge into something beautiful. Behind Jupiter at the L5 point sits the opposing army. These asteroids bear the names of Trojan heroes who defended their city against the Greek invasion. Hector commands this celestial force, joined by Paris, Aeneas, and other legendary defenders. The L5 asteroids represent Troy's eternal resistance. While the Greek camp charges ahead of Jupiter, the Trojan camp follows behind, maintaining the cosmic battle formation that Homer immortalized in verse thousands of years ago. Hector was Troy's greatest warrior, the prince who nearly drove the Greeks back to their ships. Paris sparked the entire war by stealing Helen from Sparta. Aeneas escaped Troy's destruction to found what would become the Roman Empire. Each asteroid carries these epic memories through space. This naming system creates a permanent reenactment of literature's most famous war. The two sides maintain their cosmic standoff, separated by Jupiter's bulk, forever frozen in perfect opposition around the sun. The Trojan defenders prove that space exploration and human storytelling are both ways of making sense of the vast universe around us. Nature should have created equal armies at L4 and L5, but something went wrong. The Greek camp contains significantly more asteroids than the Trojan defenders. This imbalance defies our expectations about cosmic symmetry. Mathematical theory predicts that L4 and L5 should be identical. Both points have the same gravitational environment, the same stability properties, the same capture mechanisms. Yet observations reveal a clear preference for the L4 position. Current counts show the Greeks outnumber the Trojans by a substantial margin. Some estimates suggest L4 hosts nearly twice as many large asteroids as L5. This cosmic unfairness puzzles scientists who expected perfect balance. Several theories attempt to explain this asymmetry. Perhaps Jupiter's early migration through the solar system disrupted one camp more than the other. Maybe gravitational interactions with other planets gradually emptied L5. Or possibly we haven't discovered all the L5 residents yet. This numerical mystery reminds us that even when we understand the basic physics, the universe still holds surprises that challenge our assumptions about cosmic order. These cosmic armies have been marching in formation since the solar system was young. For over 4 billion years, the Trojan asteroids have maintained their positions relative to Jupiter without missing a single step. Think about the scale of this cosmic endurance. Human civilization has existed for mere thousands of years. The dinosaurs ruled Earth for about 200 million years. Yet these space rocks have been locked in formation for 20 times longer than complex life has existed on our planet. During this epic journey, the asteroids have completed billions of orbits around the Sun. They've witnessed the formation of the rocky planets, the bombardment that scarred the Moon, the rise and fall of countless species on Earth. Through it all, they've never broken formation. This orbital stability proves that L4 and L5 are not temporary parking spots but permanent cosmic addresses. Objects can settle there and remain undisturbed for essentially forever by human standards. The Trojan asteroids represent some of the most ancient and stable communities in our solar system, preserving their formation for longer than almost anything else we know. The Trojan asteroids come in every size imaginable, from massive chunks hundreds of kilometers across to tiny pebbles barely visible in our most powerful telescopes. The largest Trojans rival major mountains in size. Hector, the biggest member of the Trojan camp, stretches over 200 kilometers from end to end. That's larger than many countries on Earth. Patroclus measures about 140 kilometers across, making it comparable to a medium-sized asteroid in the main belt. At the other extreme, countless small Trojans measure just a few kilometers or even a few meters across. These cosmic pebbles vastly outnumber their larger siblings, creating a population pyramid where tiny objects dominate the count but giant asteroids dominate the mass. This size distribution follows the same pattern we see throughout the solar system. Catastrophic collisions over billions of years have gradually broken larger objects into smaller pieces, creating more numerous fragments while preserving the total mass. The range from mountain-sized boulders to cosmic dust proves that Trojan asteroids represent a complete ecosystem of space debris that has evolved over the entire history of our solar system. Most Trojan asteroids are made from the same primitive material that formed the solar system 4.6 billion years ago. Scientists call this material carbonaceous chondrite, which is basically cosmic mud that never got processed into planets. This ancient composition makes Trojans incredibly valuable for understanding our cosmic origins. Unlike planets, which have been melted and reformed many times, these asteroids preserve the original recipe that built our solar system. Spectroscopic analysis reveals that Trojans contain water ice, organic compounds, and primitive minerals that haven't changed much since the solar nebula collapsed. They're like cosmic time capsules that have been sitting in deep freeze for billions of years. This pristine composition explains why Trojans appear so dark in telescopes. Carbonaceous material absorbs most of the sunlight that hits it, making these asteroids some of the darkest objects in the solar system. They're essentially invisible except to the most sensitive instruments. The primitive nature of Trojan asteroids makes them scientific treasures that could reveal how planets formed and where Earth's water originally came from. The Trojan asteroids didn't start their lives at L4 and L5. They were captured during Jupiter's violent youth, when the giant planet was still migrating through the early solar system and grabbing everything in its path. During the solar system's first few 100 million years, Jupiter wasn't parked in its current orbit. The giant planet wandered closer to the Sun, then drifted outward, sweeping through asteroid-rich regions like a cosmic vacuum cleaner. As Jupiter moved, it temporarily opened and closed capture windows at its L4 and L5 points. Asteroids that happened to be in the right place at the right time got swept into these gravitational pockets and trapped forever. This capture process was chaotic and violent. Jupiter's migration scattered most asteroids into the outer solar system or ejected them entirely. Only a lucky few ended up in the stable parking spots we observe today. The trapped Trojans represent survivors of this early cosmic catastrophe, refugees from Jupiter's migration that found permanent sanctuary at the planet's gravitational balance points. Trojan asteroids are among the hardest objects in the solar system to study because they spend most of their time hiding near the sun's glare. This creates a cosmic version of trying to spot a candle next to a searchlight. From Earth's perspective, the Trojans appear close to the sun in our sky. During most of the year, they're completely invisible because the sun's brightness overwhelms the faint light reflected from these dark asteroids. Astronomers get only brief windows of opportunity to observe Trojans. Just before dawn or just after sunset, when the sun is below the horizon, but the asteroids are still visible. Telescopes can catch glimpses of these elusive objects. This observational difficulty means we've probably discovered only a fraction of the total Trojan population. Thousands more asteroids likely lurk in these regions, waiting to be found during the rare moments when viewing conditions align perfectly. The hidden nature of Trojan asteroids makes them some of the least understood objects in our cosmic neighborhood, despite their scientific importance. In 2021, NASA launched an ambitious spacecraft called Lucy on a 12-year journey to visit multiple Trojan asteroids for the first time in human history. This mission will transform our understanding of these ancient cosmic artifacts. Lucy's trajectory reads like a cosmic travel itinerary. The spacecraft will fly by several Trojans in both camps, taking detailed photos and measurements of objects that have remained virtually unchanged since the solar system formed. The mission faces enormous technical challenges. Trojans orbit so far from the Sun that solar panels barely generate enough power to run the spacecraft's instruments. The journey requires multiple gravity assists and precise navigation across billions of miles. Each Trojan encounter will last only a few hours, but those brief moments will reveal details about asteroid composition, structure, and history that Earth-based telescopes could never provide. Lucy represents humanity's first direct exploration of objects that preserve the original conditions from our solar system's birth, opening a new chapter in understanding our cosmic origins. Trojan asteroids contain vast reserves of water, metals, and organic compounds that could fuel humanity's expansion into the outer solar system. These resources sit conveniently located along the main highway between Earth and the giant planets. Water is the most valuable resource for space exploration. It provides drinking water for astronauts, oxygen for breathing, and hydrogen for rocket fuel. Many Trojans contain substantial water ice deposits locked within their primitive compositions. The asteroids also harbor rare metals that are expensive and difficult to extract on Earth. Platinum group metals, used in electronics and catalysts, exist in much higher concentrations in these space rocks than in terrestrial mines. Their location at Jupiter's L4 and L5 points makes Trojans perfect cosmic gas stations. Spacecraft heading to the outer solar system could stop at these natural refueling depots to replenish supplies before continuing their journeys. The Trojan asteroids represent a trillion-dollar treasure trove of resources that could transform these ancient parking spots into humanity's first major industrial centers beyond the asteroid belt. Right now, the most powerful telescope ever built sits in empty space, far beyond the Moon's orbit. The James Webb Space Telescope has claimed permanent residence at humanity's most valuable cosmic parking spot. This isn't your typical Earth-orbiting satellite. Most space telescopes circle our planet every 90 minutes, constantly moving in and out of Earth's shadow. Webb chose a completely different strategy. It parked itself at L2, a gravitational balance point where it can observe the universe without interruption. L2 sits on the opposite side of Earth from the Sun, about 4 times farther away than the Moon. From this cosmic vantage point, Webb keeps Earth, Moon, and Sun all behind its sunshield, creating a permanently cold and dark observing environment. The parking spot comes with incredible benefits. Webb never enters Earth's shadow, so its solar panels generate power continuously. It never gets blocked by Earth or Moon, so it has an unobstructed view of deep space, and it barely uses any fuel to stay in position. This strategic location transforms Webb from a short-term experiment into a decades-long observatory that can peer deeper into space and time than any telescope before it. Space telescopes face a deadly enemy that can ruin their most sensitive measurements: heat. Even tiny temperature changes can completely destroy the precision needed to detect faint signals from distant galaxies. Webb's instruments must stay colder than the surface of Pluto to function properly. At L2, the spacecraft maintains this extreme cold naturally by keeping the Sun, Earth, and Moon all on one side of its massive sunshield. The sunshield acts like a cosmic umbrella that's larger than a tennis court. It reflects sunlight and heat away from the telescope's mirrors and instruments, creating a permanent shadow zone where temperatures drop to nearly absolute zero. This thermal isolation is impossible to achieve in Earth orbit. Satellites there constantly cycle between sunlight and shadow, causing their instruments to heat up and cool down repeatedly. These temperature swings create thermal noise that drowns out faint cosmic signals. L2 provides the ultimate deep freeze environment where sensitive infrared detectors can operate at peak performance for years without thermal interference. Earth-orbiting satellites suffer from a frustrating limitation that drives mission controllers crazy. Every orbit, they disappear behind Earth for 30 to 45 minutes, creating complete communication blackouts during critical observations. Telescopes at L2 solve this problem completely. They always maintain a direct line of sight to Earth, enabling 24-hour continuous communication. Mission controllers can send commands and receive data at any time without waiting for orbital windows. This constant connection revolutionizes how space missions operate. Instead of storing observations on board and waiting for download opportunities, L2 telescopes can stream data to Earth in real time. Scientists get results immediately instead of hours or days later. The communication advantage becomes even more valuable during critical observations. If something goes wrong during a delicate measurement, ground controllers can intervene immediately rather than waiting helplessly for the next communication pass. Continuous contact transforms space telescopes from semi-autonomous robots into remote extensions of Earth-based observatories with instant responsiveness. Staying parked at L2 requires surprisingly little effort from spacecraft engines. Unlike Earth satellites that constantly fight atmospheric drag, telescopes at cosmic balance points can maintain their positions with minimal fuel consumption. Station keeping at L2 consumes less fuel per year than some Earth satellites burn in a single day. Small thruster pulses every few weeks are enough to counteract tiny disturbances from solar wind and gravitational perturbations. This fuel efficiency extends mission lifetimes dramatically, while most Earth-orbiting telescopes run out of fuel after 5 to 10 years. L2 observatories can operate for 20 years or more before their fuel tanks run dry. The gentle nature of station keeping also reduces wear and tear on spacecraft systems. Engines fire less frequently, reaction wheels spin less often, and structural components experience fewer stress cycles. This operational simplicity allows telescope designers to focus on scientific instruments rather than complex propulsion systems, resulting in more capable observatories that last longer. L2 telescopes don't actually park at the exact balance point. Instead, they follow large oval paths called halo orbits that loop around the invisible gravitational sweet spot like cosmic NASCAR tracks. These halo orbits stretch hundreds of thousands of kilometers across. From Earth's perspective, the telescope appears to draw huge figure-8 patterns in space while maintaining its general position relative to the Sun and Earth. The orbital motion serves multiple purposes. It prevents spacecraft from getting exactly between Earth and the Sun, which would disrupt radio communications. It also provides thermal stability by ensuring all parts of the spacecraft receive similar amounts of sunlight. Halo orbits are naturally stable and require very little fuel to maintain. Small course corrections every few months keep the telescope circling the L2 point in its prescribed pattern. These giant loops transform a single parking spot into an entire neighborhood where multiple telescopes can operate without interfering with each other. For over 25 years, a spacecraft called SOCHO has been humanity's unblinking eye watching the Sun. This solar observatory parks at L1, positioned between Earth and the Sun, where it can monitor our star's activity 24 hours a day. SOA sits in the perfect spot to see solar storms before they reach Earth. Coronal mass ejections, solar flares, and other space weather events become visible hours or days before they affect our planet's magnetic field. From L1, SOA creates an artificial eclipse by blocking the Sun's bright disk with a small metal disc. This reveals the solar corona, the Sun's outer atmosphere, where most space weather originates. Earth-based telescopes can't create this effect consistently because atmospheric conditions interfere. The spacecraft has revolutionized space weather prediction by providing early warning of dangerous solar storms. This advanced notice helps protect astronauts, satellites, and power grids from radiation damage. SOCHO's quarter-century vigil at L1 proves that cosmic parking spots can host long-duration missions that provide continuous monitoring of critical space environments. The European Space Agency's Planck telescope spent 4 years at L2 creating the most detailed map ever made of the universe's oldest light. This cosmic baby picture reveals what the universe looked like just 380,000 years after the Big Bang. Planck's mission required extraordinary sensitivity to detect tiny temperature variations in the cosmic microwave background radiation. These faint signals carry information about how the first atoms formed and how cosmic structure began to emerge. L2 provided the perfect environment for this delicate measurement. Far from Earth's heat and radio interference, Planck could detect temperature differences of just millionths of a degree across the entire sky. The telescope's instruments operated at temperatures colder than deep space, requiring active cooling systems that consumed liquid helium. L2's stable thermal environment helped extend the coolant supply beyond original mission estimates. Planck's cosmic background map has become one of the most important datasets in cosmology, revealing precise measurements of the universe's age, composition, and fundamental properties. Mission designers have discovered that L2 transforms impossible observations into routine operations. The stable environment and continuous communications enable telescope concepts that would fail in other locations. Traditional Earth-orbiting missions must complete observations within single 90-minute orbits because targets disappear behind Earth. L2 telescopes can observe targets for days or weeks continuously without interruption. This observing flexibility allows for much longer exposures that reveal extremely faint objects. Deep space surveys that would take years from Earth orbit can be completed in months from L2. The location also simplifies spacecraft design. Without atmospheric drag, solar heating cycles, or communication blackouts, engineers can optimize telescopes for pure scientific performance rather than survival in hostile environments. L2 has become the preferred destination for ambitious space observatories because it eliminates most of the environmental challenges that limit telescope capabilities. L2 has become so valuable that space agencies now park multiple telescopes there simultaneously. This cosmic neighborhood hosts an international fleet of observatories that work together to study the universe. Each telescope claims its own halo orbit around the L2 point, creating a community of space observatories separated by hundreds of thousands of kilometers. They're close enough to share the same gravitational environment, but far enough apart to avoid interference. Coordinated observations between multiple L2 telescopes provide capabilities that no single observatory could achieve alone. Simultaneous measurements at different wavelengths reveal more complete pictures of cosmic phenomena. The shared location also enables cost savings through coordinated mission operations. Ground stations can communicate with multiple telescopes during single tracking passes, reducing operational overhead for each mission. This orbital community represents the emergence of L2 as humanity's primary deep space observatory platform, where international cooperation creates scientific capabilities greater than the sum of individual missions. The success of current L2 missions has convinced space agencies to build even more ambitious telescopes for this cosmic parking spot. Future observatories will search for signs of life on planets orbiting other stars. Next-generation space telescopes will be larger and more sensitive than anything ever built. Some designs feature segmented mirrors that unfold in space to create apertures larger than football fields. Only the stable environment at L2 makes such delicate deployments feasible. These future observatories will analyze the atmospheres of Earth, like planets around nearby stars, searching for chemical signatures that could indicate biological activity. Detection of oxygen, water vapor, and other biosignatures could answer humanity's most profound question: are we alone? The telescopes will also peer deeper into space and time than ever before, observing the formation of the very first galaxies and stars in the universe. L2's dark, stable environment is essential for detecting these incredibly faint and distant objects. The cosmic parking spot that started as a mathematical curiosity has become humanity's gateway to answering the biggest questions about life and the universe. What happens when you try to call someone on the far side of the moon? The call never goes through. The moon's bulk completely blocks radio signals from Earth, creating a permanent communication dead zone that spans half the lunar surface. Engineers have discovered a clever solution to this cosmic communication problem. By parking a relay satellite at the L1 point between Earth and Moon, they can create a permanent communication bridge that spans the 240,000-mile gap. L1 sits in the perfect spot to see both Earth and the Moon's far side simultaneously. A satellite there acts like a cosmic cell phone tower, receiving signals from Earth and retransmitting them to anywhere on the lunar surface. This relay capability becomes crucial for future lunar missions. Astronauts exploring the far side need constant communication with Earth for safety and coordination. Without L1 relay satellites, half the Moon remains off limits to human exploration. The Earth-Moon L1 point transforms an impossible communication challenge into a straightforward engineering problem with a permanent technological solution. Chinese space engineers proved that lunar far-side communication really works by parking a relay satellite at the Earth-Moon L2 point. This satellite enables 24-hour contact with spacecraft and rovers operating on the Moon's hidden hemisphere. The Chinese satellite sits about 50,000 miles beyond the Moon on the far side from Earth. From this vantage point, it can always see both Earth and the Moon's far side, creating an unbreakable communication link. This communication bridge made history possible. It enabled China's Chang missions to successfully land and operate on the lunar far side for the first time in human history. Without the relay satellite, these missions would have been flying blind. The satellite maintains its position with minimal fuel consumption, just like other Lagrange point spacecraft. Small thruster pulses every few weeks keep it properly aligned for continuous communication coverage. This proven communication system opens the entire Moon to human exploration, eliminating the communication blackouts that previously made half the lunar surface too dangerous to explore. NASA plans to construct humanity's first deep space truck stop at the Earth-Moon L2 point. This orbital outpost will serve as a staging area, refueling depot, and emergency shelter for crews traveling between Earth and the lunar surface. The station will follow a special orbit called NRHO, which stands for Near Rectilinear Halo Orbit. This path keeps the station relatively close to the Moon while maintaining constant communication with Earth. Astronauts can reach the station from Earth in just 4 days. From this cosmic truck stop, crews can transfer between different spacecraft designed for specific missions. Earth-to-space vehicles will dock with lunar landers, enabling astronauts to switch between specialized craft without returning to Earth. The station will also serve as an emergency shelter if lunar missions encounter problems. Crews stranded on the Moon or in lunar orbit can retreat to the L2 station and wait for rescue missions from Earth. This deep space outpost represents humanity's first permanent foothold beyond Earth orbit, establishing infrastructure that makes lunar exploration routine rather than heroic. Traditional rocket trips to the Moon burn enormous amounts of fuel, fighting Earth's gravity all the way. Smart mission planners have discovered that hopping between Lagrange points can cut fuel consumption by more than half. Instead of blasting directly from Earth to the Moon, spacecraft can follow a more efficient route that stops at gravitational balance points along the way. These cosmic rest stops allow ships to coast between destinations using minimal fuel. The journey resembles island hopping across a cosmic archipelago. Spacecraft use small amounts of fuel to reach the first Lagrange point, then coast to the next one, gradually working their way toward the Moon. This route takes longer than direct flights, but uses dramatically less fuel. The fuel savings translate directly into larger cargo capacity or extended mission duration for the same launch cost. Lagrange point highway system transforms lunar travel from an expensive sprint into an economical journey that makes the Moon accessible for routine transportation. Why can we see detailed photos of the Moon's far side today? Chinese mission planners solved the communication problem by positioning a relay satellite at the L2 balance point before sending landers to the lunar far side. The relay satellite, named Kuqiao, reached its position in 2018. This spacecraft created humanity's first permanent communication link to the Moon's hidden hemisphere, enabling real-time control of far-side missions. With communication established, China successfully landed the Chang'e 4 mission on the far side in 2019. The lander and rover transmitted stunning images and scientific data through the relay satellite back to Earth. This communication system proved so successful that China expanded it for additional far-side missions. Multiple spacecraft now operate on the lunar far side with continuous Earth contact through the L2 relay. The Chinese communication breakthrough demonstrates that Lagrange points provide practical solutions to real space exploration challenges, not just theoretical parking spots. Future Earth-Moon transportation will flow through Lagrange point hubs that function like cosmic distribution centers. These space stations will sort cargo, transfer crews, and coordinate traffic between Earth and multiple lunar destinations. Think of these hubs like major airports that handle connecting flights. Spacecraft from Earth will dock at Lagrange point stations, where crews and cargo get transferred to lunar shuttles heading to specific destinations on the Moon's surface. This hub-and-spoke system makes lunar operations much more efficient. Instead of launching separate missions from Earth to each lunar destination, one large cargo ship can supply multiple Moon bases through the Lagrange Point Distribution Center. The stations will also provide maintenance, refueling, and emergency services for spacecraft operating in the Earth-Moon system. They become cosmic service stations that keep the transportation network running smoothly. These logistics hubs transform scattered individual missions into an integrated transportation system that supports permanent human presence throughout the Earth-Moon region. Earth-Moon Lagrange points face a problem that doesn't exist around the Sun and Jupiter. The Sun's gravity constantly disturbs these balance points, making them less stable than their solar system cousins. Solar gravitational effects act like a cosmic wind that gradually pushes objects away from Earth-Moon balance points. Spacecraft parked there need regular course corrections to counteract this slow drift, unlike the rock's solid stability of Jupiter's Trojan asteroids. The instability isn't catastrophic. Spacecraft can maintain position at Earth-Moon Lagrange points for years with modest fuel consumption. But they can't park there indefinitely without occasional thruster burns to stay in place. Mission planners have turned this challenge into an advantage. The gentle instability makes it easier to transfer between different Lagrange points, enabling spacecraft to hop from one balance point to another with minimal energy. This controlled instability creates a dynamic transportation network where spacecraft can move efficiently between multiple cosmic parking spots in the Earth-Moon system. Space weather poses a serious threat to astronauts, satellites, and power grids on Earth. Lagrange points in the Earth-Moon system provide perfect locations for solar storm monitoring stations that give advance warning of dangerous space weather. L4 and L5 points offer side-angle views of the Sun that reveal solar activity before it affects Earth. Monitoring satellites at these locations can detect coronal mass ejections and solar flares while they're still days away from our planet. This advance warning time allows astronauts to take shelter, satellite operators to put spacecraft in safe mode, and power companies to prepare electrical grids for geomagnetic storms. The monitoring network will also track space debris and asteroids that might threaten Earth or lunar operations. Multiple observation points provide better tracking accuracy than single satellites. These cosmic watchtowers transform the Earth-Moon Lagrange points into humanity's first line of defense against threats from space. Advanced mission planners have discovered that invisible mathematical pathways connect different Lagrange points throughout the Earth-Moon system. Spacecraft can follow these weak stability boundaries to travel between balance points using almost no fuel. These pathways exist because of subtle gravitational interactions between Earth, Moon, and Sun. They create natural shipping lanes through space where spacecraft can coast from one destination to another with minimal propulsion. The mathematical routes are incredibly complex and require supercomputer calculations to map precisely. But once plotted, they enable spacecraft to reach multiple destinations on a single fuel budget. Some pathways connect Earth-Moon Lagrange points directly to solar system balance points, creating cosmic highway networks that span millions of miles. These gravitational superhighways represent the future of efficient space transportation, where mathematical precision replaces brute force rocket power for interplanetary travel. Permanent lunar bases will depend on Lagrange point stations for supplies, communications, and emergency backup. These cosmic supply depots make the difference between short-term expeditions and permanent human settlement. Regular cargo shuttles will ferry supplies from Lagrange point warehouses to lunar surface bases. This system provides much more flexibility than direct Earth-to-Moon deliveries, which must hit precise launch windows and arrive at exact times. The space stations will also maintain emergency escape vehicles that can quickly reach lunar bases if evacuation becomes necessary. Crews facing medical emergencies or equipment failures can retreat to the safety of the Lagrange point stations. Communication relays at multiple balance points will provide redundant contact with lunar bases, ensuring that crews never lose touch with Earth even if individual satellites fail. This support network transforms lunar bases from isolated outposts into well-connected communities that can grow and thrive with regular supply deliveries and constant Earth contact. Lagrange points provide perfect locations for manufacturing facilities that take advantage of zero gravity and vacuum conditions to create materials impossible to make on Earth. These cosmic factories will produce ultra-pure crystals, advanced alloys, and specialized components. Zero gravity eliminates many manufacturing problems that plague Earth-based production. Metal alloys don't separate by density, crystals grow without gravitational stress, and chemical reactions proceed without convection interference. The vacuum environment provides automatic contamination control that would cost billions to achieve in Earth laboratories. Manufacturing processes that require ultra-clean conditions become routine in space. Products from these space factories will be incredibly valuable on Earth. Perfect crystals for electronics, advanced materials for aerospace applications, and specialized medical devices could justify the cost of space-based production. These orbital manufacturing centers represent the beginning of space industrialization, where the unique environment beyond Earth's atmosphere becomes humanity's newest factory floor. Mars has its own cosmic companions, but they're much lonelier than Jupiter's massive asteroid armies. Only a handful of space rocks have claimed parking spots at Mars' L4 and L5 balance points, creating small communities in the red planet's gravitational neighborhood. These Martian Trojan asteroids prove that cosmic parking spots exist throughout the solar system, not just around giant planets like Jupiter. Any planet with enough mass can create stable balance points where smaller objects can park permanently. The first Martian Trojan was discovered in 1990, surprising astronomers who weren't expecting to find cosmic hitchhikers around such a small planet. Since then, several more have been found, though the total population remains tiny compared to Jupiter's thousands. Why so few compared to Jupiter? Mars is much smaller and lighter than the giant planet, so its gravitational influence is weaker. The balance points exist, but they're less stable and harder for asteroids to find and stick to. These lonely Martian companions demonstrate that cosmic parking spots are universal features of planetary systems, even when the communities that use them remain small and exclusive. Far beyond Mars, in the cold outer reaches of our solar system, Neptune hosts its own collection of Trojan asteroids that have been hiding in plain sight for billions of years. These distant companions share the ice giant's orbit in a cosmic dance that spans 165 Earth years. Neptune's trojans represent some of the most ancient objects in our solar system. They've been locked in their current orbits since the planets finished forming, preserving original conditions from the solar system's youth. The discovery of Neptune's trojans came as a major surprise to astronomers. The ice giant sits so far from the Sun that its gravitational balance points seem too weak and too disturbed by other planets to maintain stable parking spots. Yet these cosmic hitchhikers have survived for 4.5 billion years in Neptune's L4 and L5 regions. They follow orbital resonance patterns that keep them synchronized with Neptune's motion, like cosmic clock gears that never lose time. Neptune's Trojan collection proves that even the most distant planets can maintain stable gravitational communities across cosmic time scales. Saturn's moon system contains its own network of cosmic parking spots where tiny moons have found permanent homes. These miniature satellites demonstrate that Lagrange points work at every scale, from asteroid-sized objects to planet-sized systems. The most famous examples orbit alongside Saturn's larger moons, forming perfect triangular arrangements that would make any geometry teacher proud. Small moons park exactly 60 degrees ahead of and behind their larger companions, following the same mathematical rules that govern Jupiter's asteroids. These tiny satellites are often irregularly shaped chunks of rock and ice, probably captured asteroids or fragments from ancient collisions. They've found gravitational safe harbors where they can orbit Saturn without getting flung into space or crashing into larger moons. Saturn's complex moon system creates multiple sets of balance points at different distances from the planet. This creates a layered network of cosmic parking spots that extends from close to Saturn's rings all the way out to its most distant moons. The Saturn system reveals that cosmic parking spots can create elaborate orbital architectures where dozens of objects maintain stable relationships across millions of cubic miles of space. Saturn's moon Tethys has achieved something remarkable in the cosmic community. It shares its orbit with two smaller companions that maintain perfect triangular formation as all three race around Saturn together. The two companion moons are named Calypso and Telesto. Calypso parks at Tethys L5 point, trailing behind the larger moon. Telesto occupies the L4 position, leading Tethys in their shared orbital path around Saturn. This three-body system demonstrates gravitational harmony in action. All three moons maintain their triangular arrangement while completing one orbit around Saturn every 1.9 Earth days. They've held this formation for millions of years without breaking ranks. The arrangement showcases the mathematical beauty built into celestial mechanics. Three objects of different sizes following the same orbit while maintaining perfect geometric relationships across hundreds of thousands of miles. Tethys and its companions prove that cosmic parking spots can support permanent multi-body communities where mathematical precision creates lasting stability. Another Saturn moon named Dione rules over its own cosmic court, complete with two small attendant moons that serve as permanent escorts. These smaller satellites follow Dione's orbit while maintaining respectful distances at the L4 and L5 balance points. The escort moons are called Helene and Polydeuces. Helene leads Dione in orbit, positioned at the L4 point ahead of the larger moon. Polydeuces follows behind at L5, completing the triangular formation that defines these cosmic relationships. This royal court arrangement has persisted for eons. The three moons maintain their orbital choreography while circling Saturn every 2.7 Earth days. never breaking formation or abandoning their assigned positions. The size differences make this system particularly striking. Dione measures over 1,100 kilometers across, while its escorts are tiny irregular chunks only 30 kilometers or less in diameter. Yet gravitational mathematics treats all three as equal partners in the orbital dance. Dion's court demonstrates that cosmic parking spots can create hierarchical communities where large and small objects coexist in stable, long-term relationships. Not all residents of cosmic parking spots are solid objects you can photograph. Some Lagrange points throughout the solar system collect invisible clouds of microscopic dust particles that create ghostly congregations in space. These dust clouds form when tiny particles get trapped in the same gravitational balance points that capture larger asteroids and moons. Solar radiation and magnetic fields help concentrate the particles into distinct clouds that can persist for thousands of years. The dust congregations are incredibly difficult to detect because individual particles are smaller than the width of human hair. They reveal themselves only through subtle effects on sunlight or spacecraft instruments that pass through them. Some dust clouds may be the remnants of ancient collisions between larger objects at Lagrange points. When asteroids or moons crashed together in these gravitational sweet spots, the debris stayed trapped in the same region instead of dispersing throughout space. These invisible cosmic communities show that balance points can collect and organize matter at every scale, from mountain-sized asteroids down to microscopic grains of dust. How did all these cosmic parking communities form in the first place? The answer lies in the chaotic early days of our solar system, when a swirling disk of gas and dust was slowly condensing into the planets and moons we see today. As planets formed and grew larger, their gravitational fields created the first Lagrange points in the solar nebula. These balance points acted like cosmic vacuum cleaners, collecting nearby dust and small rocks that happened to drift into their gravitational neighborhoods. The process was neither gentle nor organized. Early planetary migration scattered objects throughout the solar system, but some lucky asteroids and dust particles ended up in the right place at the right time to get captured by newly formed balance points. Jupiter's migration was particularly important for populating Lagrange points throughout the solar system. As the giant planet wandered inward and then outward during its early years, it scattered objects that later got trapped at various balance points around other planets. This ancient assembly process explains why cosmic parking communities exist throughout our solar system, each one a fossil record of the violent processes that built our planetary neighborhood. Some of the most stable cosmic communities don't park at traditional Lagrange points, but instead follow complex orbital resonances that create their own forms of gravitational stability. These resonant relationships work like cosmic clockwork, where different orbital periods create mathematical harmony. A 3-to-2 resonance means one object completes exactly 3 orbits while its partner completes 2. This mathematical relationship creates predictable gravitational nudges that can either stabilize or destabilize orbits, depending on the specific circumstances. Pluto and Neptune follow a 3-to-2 resonance that keeps them in gravitational harmony despite their crossing orbital paths. This resonant relationship ensures they never come close enough to collide, even though their orbits overlap on paper. Similar resonant relationships create stable parking zones throughout the solar system. Objects trapped in these mathematical patterns can maintain their positions for billions of years, just like traditional Lagrange point residents. These resonant communities prove that gravitational stability can emerge from mathematical relationships that are far more complex than simple balance points. The Kepler Space Telescope has detected hints of cosmic parking communities around other stars, suggesting that planets in alien solar systems might share orbits just like asteroids do around Jupiter. These potential Trojan planets would be full-sized worlds parking at the L4 and L5 points of larger planets in distant star systems. The gravitational relationships would be identical to our solar system's asteroid communities, but scaled up to planetary proportions. Detection of Trojan planets requires incredibly precise measurements because the planets appear as tiny blips in their host star's light. Kepler identified several candidate systems where the data suggests planets might be sharing orbits in Lagrange point configurations. Confirming these detections remains challenging with current technology. The signals are so faint that astronomers need years of observations to distinguish genuine Trojan planets from measurement noise or other astronomical phenomena. The possibility of Trojan planets in other star systems suggests that cosmic parking communities might be common features of planetary systems throughout the galaxy. Earth has its own cosmic parking spots, but most of our planet's Lagrange point visitors are temporary guests rather than permanent residents. Small asteroids occasionally get captured at Earth's L4 and L5 points for a few decades before drifting away again. These temporary visitors follow complex orbital paths that astronomers call horseshoe orbits. The asteroids appear to chase Earth around the Sun, sometimes getting ahead of our planet and sometimes falling behind in an endless cosmic game of tag. The instability of Earth's Lagrange points comes from the Moon's gravitational influence, which constantly disturbs the balance points and prevents long-term asteroid capture. Objects that might otherwise park permanently at L4 or L5 get nudged away by lunar gravity. Some near-Earth asteroids spend centuries switching between different types of orbits relative to our planet. They might park temporarily at L4, then shift to a horseshoe orbit, then visit L5 before eventually escaping to other parts of the solar system. Earth's temporary cosmic companions demonstrate that not all Lagrange point communities are permanent, and that gravitational relationships can be dynamic and ever-changing. Jupiter's 4 largest moons create their own network of cosmic parking spots where ring particles and dust grains collect into faint concentrations. These miniature versions of Lagrange communities exist within Jupiter's complex gravitational environment. The Galilean moons, Europa, Ganymede, and Callisto, each generate their own sets of balance points as they orbit the giant planet. Ring particles from Jupiter's faint ring system sometimes get trapped in these locations, creating temporary concentrations of cosmic dust. These dust congregations are incredibly faint and require sensitive instruments to detect. They appear as subtle enhancements in the density of ring material at specific locations relative to each moon's orbit around Jupiter. The particles don't stay trapped permanently because Jupiter's intense radiation environment and complex gravitational field eventually disperse the concentrations. But new particles continuously replace the old ones, maintaining ongoing communities of cosmic dust. These miniature Lagrange communities within Jupiter's moon system demonstrate that balance points can exist within balance points, creating nested hierarchies of gravitational organization. Why haven't we found more cosmic parking communities throughout the solar system? The answer lies in the incredible difficulty of detecting small, dark objects that spend most of their time hiding in the glare of much brighter celestial bodies. Most Lagrange point objects are tiny and reflect very little sunlight, making them essentially invisible except to the most powerful telescopes under perfect viewing conditions. They're like trying to spot black pebbles scattered across a football field at night. The object's orbital positions make detection even harder. They often appear close to bright planets or stars in our sky, where their faint light gets overwhelmed by much brighter sources. Astronomers can only spot them during brief windows when viewing geometry aligns perfectly. Advanced asteroid survey programs are gradually finding more Lagrange objects as telescope sensitivity improves and search techniques become more sophisticated. Each discovery suggests that many more objects remain hidden, waiting for future detection. The hidden population of cosmic parking communities probably contains thousands of objects throughout our solar system, representing a vast ecosystem of gravitational relationships that we're only beginning to explore. Imagine living in a giant spinning cylinder floating in space, complete with parks, lakes, and artificial weather systems. These massive space habitats could house millions of people at L4 and L5 balance points, creating humanity's first true space cities. The concept comes from physicist Gerard O'Neill, who designed rotating cylinders that use centrifugal force to create Earth-like gravity. Residents would live on the inner surface of these cosmic tubes, held in place by the spinning motion, just like being pressed against the wall of a spinning carnival ride. These space habitats would be enormous structures, stretching for miles and housing complete ecosystems: agriculture, manufacturing, recreation. And residential areas would all exist within the rotating environment, making these communities completely self-sufficient. L4 and L5 provide perfect locations for these mega structures because they offer gravitational stability without interference from planetary gravity fields. The habitats could maintain their positions indefinitely while generating their own artificial gravity through rotation. These spinning space cities represent humanity's first step toward becoming a truly spacefaring civilization that no longer depends entirely on planetary surfaces for survival. What if you could build a solar power station that operates 24 hours a day, 365 days a year, with no weather interruptions? L5 offers exactly these conditions for massive solar power installations that could revolutionize energy production for Earth. Unlike Earth-based solar panels that lose efficiency due to clouds, atmosphere, and nighttime darkness, space-based solar collectors would receive constant, unfiltered sunlight. The energy output would be at least 10 times higher than equivalent installations on Earth's surface. These cosmic power plants would use enormous arrays of solar collectors to capture sunlight and convert it into microwave beams that could be transmitted wirelessly to receiving stations on Earth. The technology already exists in prototype form. L5 provides the perfect platform for these installations because spacecraft there never enter Earth's shadow and maintain stable positions relative to both Earth and Sun. The power transmission would be constant and reliable. This space-based solar revolution could provide clean, unlimited energy for Earth's growing population while eliminating the need for fossil fuels or dangerous nuclear installations. Mining asteroids sounds like science fiction, but the economics are becoming irresistible. A single metallic asteroid contains more platinum than has ever been mined on Earth, and L4 and L5 balance points offer perfect locations for processing these cosmic treasure troves. The plan involves capturing asteroids from the main belt and slowly moving them to L4 or L5 processing stations. The journey might take years, but robotic spacecraft can guide asteroids along fuel-efficient trajectories to these cosmic industrial parks. Once parked at balance points, the asteroids become stationary targets for automated mining equipment. Giant robotic systems would break down the rocks, extract valuable metals, and process raw materials into useful products for space construction projects. The extracted materials would never need to be lifted from Earth's gravity well, making space-based construction projects dramatically cheaper than hauling materials up from our planet's surface. These asteroid mining operations could provide unlimited raw materials for expanding human civilization throughout the solar system while making space-based industry economically competitive with Earth production. Manufacturers dream of producing materials in perfect vacuum with zero gravity interference. L4 and L5 balance points offer these ideal conditions for creating ultra-pure crystals, advanced alloys, and specialized products impossible to make on Earth. Zero gravity eliminates many manufacturing defects that plague Earth-based production. Metal alloys don't separate by weight, crystals grow without gravitational stress, and delicate assembly processes proceed without objects falling or shifting unexpectedly. The perfect vacuum environment provides automatic contamination control that would cost billions to achieve in terrestrial clean rooms. Chemical processes that require ultra-pure conditions become routine in the sterile environment of space. Products from these space factories would command premium prices on Earth. Perfect semiconductor crystals for electronics, specialized metal alloys for aerospace applications, and ultra-pure pharmaceuticals could justify the transportation costs. These orbital manufacturing centers represent the beginning of space industrialization, where the unique environment beyond Earth's atmosphere becomes humanity's most advanced factory floor. Earth faces a constant threat from asteroids and comets that could cause devastating impacts. L4 and L5 balance points provide ideal locations for asteroid defense systems that could detect and deflect potentially dangerous objects years before they threaten our planet. These cosmic watchtowers would host networks of powerful telescopes that scan the solar system continuously for objects on collision courses with Earth. The advance warning time from these positions could extend to decades for some threats. If a dangerous asteroid is detected, defensive spacecraft stationed at the balance points could intercept it far from Earth using nuclear explosives, solar sails, or gravitational tugboats to alter its trajectory slightly but decisively. The key advantage is distance and time. Small course corrections applied years in advance can turn a direct hit into a harmless miss, while last-minute interventions from Earth orbit might be too little, too late. This planetary defense network transforms L4 and L5 from passive observation posts into active guardians that could prevent the next major extinction event. Sending spacecraft to the outer planets requires enormous rockets and massive fuel loads when launching from Earth's deep gravity well. Assembly and fueling operations at L4 and L5 could make interplanetary missions much more practical and affordable. These space-based shipyards would construct large spacecraft from materials mined and processed at the balance points. Without fighting Earth's gravity, engineers could build much larger and more capable vessels for deep space exploration. Fuel production facilities at L4 and L5 would extract water from asteroids and split it into hydrogen and oxygen for rocket propulsion. This eliminates the need to lift massive fuel loads from Earth's surface at enormous cost. Large expedition ships assembled in space could carry substantial crews, scientific equipment, and supplies for multi-year journeys to Jupiter, Saturn, and beyond. The missions would be more like ocean voyages than desperate sprints. These cosmic shipyards transform interplanetary exploration from heroic one-shot missions into routine transportation operations that support permanent human presence throughout the solar system. Some scientific experiments require enormous size, perfect stability, and complete isolation from vibrations. L4 and L5 balance points could host gravitational wave detectors, radio telescope arrays, and other instruments that are impossible to build on planetary surfaces. Gravitational wave detectors work by measuring incredibly tiny distortions in space itself. These measurements require laser interferometers stretching across millions of miles with perfect stability. Only the vacuum and stability of Lagrange points can provide these conditions. Radio telescope arrays could span entire regions around L4 and L5, creating virtual telescopes larger than Earth itself. These cosmic instruments could detect signals from the most distant galaxies and search for radio transmissions from alien civilizations. The perfect isolation from Earth's radio interference would allow detection of incredibly faint signals that get drowned out by terrestrial electromagnetic noise. These space-based instruments could revolutionize astronomy and communications. These scientific installations transform L4 and L5 into humanity's ultimate research platforms, where the unique environment of space enables discoveries impossible anywhere else. Who owns the cosmic parking spots? As L4 and L5 develop into major industrial and residential centers, humanity will need entirely new forms of international law and governance to manage these space territories. Unlike Antarctica, which belongs to no single nation, Lagrange point settlements could become permanent homes for millions of people who need citizenship, legal systems, and democratic representation. Traditional Earth-based governments may not be adequate for space-based societies. The settlements might develop their own forms of government adapted to the unique conditions of space life. Constitutional conventions in zero gravity, elections conducted across millions of miles, and legal systems that account for three-dimensional territorial boundaries. International cooperation will be essential because no single nation has the resources to develop these regions alone. Space-based settlements could become humanity's first truly international territories governed by coalitions of Earth nations. These new forms of space governance could serve as testing grounds for international cooperation that eventually helps solve conflicts and resource disputes back on Earth. The first residents of L4 and L5 won't be human pioneers, but rather armies of construction robots that spend decades building infrastructure before people arrive. This automated construction phase makes space settlement much safer and more practical. Advanced 3D printing technology could manufacture entire space habitats from asteroid materials using robotic systems controlled from Earth. The robots would work continuously without life support, radiation shielding, or rest breaks that human workers require. These robotic construction teams could operate for years or decades, gradually assembling the massive infrastructure needed to support human communities. By the time people arrive, complete cities would be waiting for them. The robotic phase also serves as a testing ground for space-based life support systems, manufacturing processes, and transportation networks. Problems can be identified and solved before human lives depend on these systems. This stage development approach transforms space settlement from dangerous pioneering expeditions into carefully planned migrations to pre-built communities with proven infrastructure. L4 and L5 settlements represent more than just new places to live. They mark humanity's transition from a single-planet species to a true spacefaring civilization that can survive and thrive throughout the solar system. These space-based communities would be completely self-sufficient, capable of surviving even if Earth became uninhabitable due to natural disasters or human conflicts. They serve as backup copies of human civilization in multiple locations. The technological and social innovations developed at Lagrange points would eventually enable settlements throughout the solar system. Asteroid belt mining stations, Mars colonies, and even generation ships to other star systems become possible. Children born at L4 and L5 would be the first true space natives, adapted to zero-gravity and vacuum environments in ways that Earth-born humans cannot imagine. They represent the beginning of human speciation for space environments. The cosmic parking spots discovered by 18th century mathematics become launching pads for humanity's expansion into the galaxy, transforming our species from planetary residents into citizens of the cosmos.